rate in and rate out. In calculus, an extension of net change and accumulation is rate in and rate out. Instead of problem solving with only one rate of change, now the problems are going to contain two of them. And there will be times when the rate at the beginning, or the rate in, is different than the rate at the end of the problem, or the rate out. Let's get started with an example. The rate at which people enter an amusement park on a given day is modeled by the function e of t, which is equal to 15,600 divided by the polynomial t squared minus 24t plus 160. The rate at which people leave the same amusement park on the same day is modeled by this rational function, L of t, which is equal to 9,890 divided by the polynomial t squared minus 38t plus 370. Both E of t and L of t are measured in people per hour, and time t is measured in hours after midnight. These functions are valid for t values or time values between 9 and 23, including both endpoints, which are the hours during which the park is open. At time t equals 9, there are no people in the park. This means that at 9 a.m., the park opens. So therefore, there are no people that exist in the park prior to that time. And that t being less than or equal to 23 means that the park closes at 11 p.m. Now let's look at the first question that we need to answer. How many people have entered the park by 5 p.m.? Round your answer to the nearest whole number. And also note that the park closes at 11 p.m. Before we start solving this problem, it's important to point out that the question is asking for how many people, or the amount of people that entered the park by 5 p.m., which is different than how many people enter the park specifically at that time. Therefore, it's requiring us to integrate. So we're going to set up the definite integral with the function for entering the park. So that's the E of t problem. And because it opens at 9 a.m., we're going to go from t being 9 up to 5 p.m., which is 17. And then if we take E of t and substitute it into our integral, we'll end up having the integral from 9 to 17 of 15,600 divided by the polynomial t squared minus 24t plus 160. And we're going to integrate with respect to t. And now we can enter this integral into our calculator in order to solve it. So we're going to use math. We're going to choose option 9. And our lower bound is 9. Our upper bound is 17. And we're going to put in there 15,600 divided by, and we have to open a parenthesis for the denominator. You can either elect to use t throughout, just as the function does here, or you can use an x instead. So I'm going to do x squared minus 24x plus 160, and then I'm going to close that parenthesis for the denominator. And then, because I used x instead of t, I need to integrate with respect to x. And then when we solve this, we get the solution, 6,004 and about 270 thousandths. And what that means is that about 6,004 people have entered the park by 5 p.m. Now let's answer question B. The price of admission to the park is $15 until 5 p.m., or time is equal to 17 that we've found before. After 5 p.m., the price of admission to the park is $11. How many dollars are collected from admissions to the park on the given day. Round your answer to the nearest whole number. Let's get started. The first step in solving this problem is going to be to use the information that we solved for in the first part of this question, which is the total admission up until 5 p.m. Well, that was 6,004 people, and the admission price for all of those people was $15. So we can determine how much money was collected by multiplying $15 times 6,004, and that ends up equaling $90,060. And once we have this value, we can set up an integral for the remaining hours that the park was open. So that will be from t equals 17 to 23 of e of t dt, and we can multiply that integral by the $11 for admission. The next step is to integrate and evaluate. Since we can't integrate this function directly, we can substitute it into our calculator just as we've been doing in order to calculate our answer. So we have 90,060 plus 11, which is the cost per ticket after 5 p.m., times the integral, so that's option 9 here, from 17 up to when it closes, which is 23, which corresponds to 11 p.m. And then we have 15,600 divided by the quantity, or the open a parenthesis for the entire polynomial. I'm going to use x values when substituting it into the calculator. It's completely up to you with how you would like to substitute it in. Just make sure that the variable that you use in your function is the same variable that you are integrating with respect to. So I have x squared minus 24x plus 160, close the parenthesis for the polynomial, and then we're differentiating for me with, integrating with respect to x because I used x values here. And then when we press the equal sign, we get $104,044 if we round it to the nearest whole number as the question states. And here there's an extra step that's showing, which would be directly evaluating the second part of this, or the integral, and then adding afterwards. But we still get the same solution, $104,044. Now let's look at part C of this question. Let h of t be equal to the integral from 9 to t of e of x minus L of x. And we're going to integrate with respect to x. For t values between 9 and 23, including our endpoints, the value h of 17 to the nearest whole number is 3,725. Find the value of h prime of 17 and explain the meaning of h of 17 and h prime of 17 in the context of the park. Let's get started. Did you notice anything familiar about the first line of this part of the problem? This actually models the fundamental theorem of calculus part 1. So we can use that to differentiate. If h of t is equal to the integral of e of x minus L of x, then h prime of t will actually equal e of x minus L of x. Or in other words, h prime of t is equal to e of t minus L of t. Therefore, we can substitute t equals 17 directly into h prime of 17, which is again e of 17 minus L of 17. So we can substitute 17 into both of these rational functions and then evaluate it. So we have 15,600 divided by 17 squared minus 24 times 17 plus 160, close the parenthesis, and then we have subtraction. And then we're going to have 9,890 divided by 17 squared minus 38 times 17 plus 370. And if we evaluate this, we'll end up getting negative 380 and 281 thousandths about, to simplify it. And the meaning of h prime of 17 is that the number of people in the park was decreasing at a rate of approximately 380 people per hour. And if we're given that h of 17 is equal to 3,725, this means that there will be 3,725 people in the park when time is 17, or at 5 p.m. Now let's look at part D. At what time t for t values between 9 and 23, including both endpoints, does the model predict that the number of people in the park is a maximum? Well, a maximum usually occurs when the derivative is set equal to 0. Well, we know that h prime of t is equal to e of t minus L of t, and we can set it equal to 0 and solve. So our h prime of t is equal to e of t, which is 15,600, divided by the polynomial t squared minus 24t plus 160, and then we're subtracting 9,890 divided by the polynomial t squared minus 38t plus 370. Okay, so this is our derivative, and we're going to substitute it into our graphing calculator and graph it, and we're going to find out where it equals 0. So let's do that part. So we have y equals, and we're going to type in exactly what we wrote here. 15,600 divided by, instead of t squared, I'm going to use x's, so x squared minus 24x plus 160, close parenthesis, minus 9,890 divided by x squared minus, delete that option because I got to get out of the exponent, minus 38x plus 370, close the parenthesis for the denominator and then the parenthesis for the entire rational function. And then if we go to graph, yeah, I didn't think it would appear here. So let's adjust our window. Let's try something. Well, our x values generally range from 9 to 23. So I'm going to make it -1. And I'll go up to 25. And I'll make the x scale be 2. And then y minimum, I'll keep at -10. But let's try making our y maximum at, say, 2,000. And let's make the y scale be every 200. Mark it on the axis. Let's see what that does. Graph. Okay, here's what our derivative looks like, and we're trying to find where the derivative is equal to 0. Notice it only crosses the x-axis right here, so we can go to second calc, and we're finding the 0. And we've got to go to the left of it, and this is fine. And then we got to go to the right, so a little below. That's definitely below, and then when it appears in the middle. Okay, so our 0 is at 15 and about 795 thousandths. Could also do 794 thousandths. And that's the solution to this problem. And this actually means that at about 1500, or I'm even thinking closer to the 1600th hour, so it's between 3 p.m. and 4 p.m. that this maximum value occurs at. It's probably closer to, say, 3:45 or 3:50, or 3:50 p.m. as the actual time of the day.